Hello, I wanted to show off the progress I've been making on text support in my Vulkan game engine project. Here we have 3 text layouts. The top one is mixed script with Latin, emoji, Arabic, and Japanese, and it has word wrap. The middle one is entirely Arabic, and it is also word wrapped, and the bottom is entirely Latin text and is not long enough to be triggering word wrap. I'm really quite pleased with how this is turning out. You can see I'm going to walk around a bit, do some stuff in the game world. If you know me, if you've spoken to me in any way, like in the past while, I've been really excited about a set of libraries that have appeared on the scene that are allowing me to do this to the extent that I am. Because most game engine projects will pull in free type as a dependency, and then go through each code point, if you're lucky, code points, each code point in a string and attempt to find a glyph for that code point, and then rasterize it with free type, and then blip that somewhere. So yeah, if the code points you have aren't covered by the specific font you have loaded, you're not going to get results out of that. So you're limited to what like one font can support, unless you do like really like a lot more work. Like you can do a lot more work, of course, but like, but more than that. Not every code point is a visible code point, and their code points are not necessarily characters. There are things that we would consider characters that are made up of multiple code points. So you get in code points versus graphemes, and there's all sorts of depth and complexity to that. So that is a really insufficient solution. Really insufficient solution. So what I'm doing here is I'm using a set of libraries that let me handle that better. Now, what a lot of, oh, that, can I line that up? There we go. Now, what a lot of from scratch game engine projects will do is rely on system libraries for this. Specifically on Windows, you could use DirectWrite if you're using Direct2D. There's GDI, which I think you can use in various different situations. And then there's Uniscribe. All sorts of those are all different sorts of, they all fit like different niches, and they're all like, have different capabilities. And like Uniscribe I don't think even does rasterization at all. It's purely just layout and shaping. Anyway, I'm on Linux, and I want to support Windows and Linux at the bare minimum. Potentially support Mac OS as well in the future, right? Like, relying on these, yeah, that's not an option. The alternative would be to use Harfbuzz for shaping, which is getting into the complexities of what shaping versus layout is yeah, but then like you have to build your own layout engine on top of that, which is possible. I've experimented with that in the past in other projects. It's a very steep task. And I'm someone with like a fair bit of text handling knowledge to begin with. Like, it's complicated. So I'm using a set of libraries called Parlay, Swash, and Zeno, whatever, all by the same author. They're all like bundled together. They're like kind of like made for each other, for use with each other. And I've been really excited about these for a while, even before I started using them for this, because having a cross-platform Rust native, specifically cross-platform Rust native text, layout, and shaping engine that has good support for all sorts of text is a really big deal. Like, really big deal. Because before, I'm not aware of any single cross-platform library that fits that specific niche of being like a drop-in text layout and shaping engine that you can just pull into your project and build and deploy to multiple platforms and whatever. Like, I'm not personally aware of anything that fits that bill. Like, there are definitely things that you could use, but they would be difficult, and they're like built into other things, and like all sorts of just, or require you to build a lot of logic yourself, like all sorts of stuff. So I'm very excited about these libraries existing, and so I'm using them here. But they just provide layout and shaping, which is a whole rabbit hole of complexity and that's how like this Arabic text looks correct, stuff like that. That's why. But I'm still responsible for like getting that on screen. I'm still because this is my own Vulkan renderer, and I have to go from, I have a text layout with a bunch of information about lines and glyph runs and like stuff like that, and be like, get that on screen. So something that makes this more complicated. So the easy solution here is just render each glyph to memory, upload that rendered bitmap to GPU memory, and then display that basically as a sprite, right? That's the easiest way to think about it, and that's really easy, and it works. But you don't really want to be doing that, because if we run this again, so this is a fair amount of text. It's not a crazy amount, but it's still a fair amount, right? Like, it's not, this amount of text is nothing to scoff at, and would start to become a problem with that specific approach. Actually, this text would be a problem. This amount of text would be a problem. So the thing is that glyph rasterization is, you just have to assume it's slow. There are a bunch of things you can do to make it faster, and the fastest way to do it would just be to not rasterize that on the glyph at all, on the CPU at all, but to turn it into, turn the shapes of the glyphs into meshes, and then the mesh you upload, and then you render it just like any other part of your pipeline, and that's it. And that's the easiest, and not the easiest, that would be the fastest way. Right now, with like what this current state of the art is, that would be the fastest way. But that's a lot of work, and there's a lot of extra complexity there. So what I'm doing is I'm still rasterizing the glyphs on the CPU side, and uploading that to GPU memory, but I'm doing a whole lot of stuff to avoid doing too much work. So we want to minimize the amount of rasterization we do of glyphs, and we want to minimize the amount of GPU memory we use, because the more GPU memory we use, we have a finite amount of it, we will run out, and we have to like set up ahead of time, like at the beginning, like this is how much I want to use for this specific buffer. So like it's a trade-off of how much you have to begin with. And secondly, we don't really want to have to be uploading a whole bunch of text to the GPU every frame. So we do a bunch of caching, and there's two layers of caching here, in fact. There's the CPU side cache, and there's the GPU side cache. So the GPU cache is cleared every frame, and that lets the way that I use GPU memory simply just be a bump allocator, effectively. That's just all it is. It's just basically a bump allocator. Because if I was caching glyphs across frames in GPU memory, then I'd have to worry about like adding and removing glyphs from the cache in GPU memory, which means I have to deal with holes and then filling new glyphs into the holes where old glyphs used to be, and I have to worry about sizes. And now fragmentation is a massive issue, and like memory allocation is like just this huge field of problems. It's really interesting and difficult topic that I don't want to deal with. I don't want to deal with because that can be so much trouble. So the GPU cache, the glyph cache on the GPU memory is cleared each frame. So what this means is not that, oh, we use a glyph and then we don't have to upload that into GPU memory ever again. No, what it means is we can reuse that specific chunk of glyph data multiple times within the same frame. So there are a bunch of O's in this letter, the letter O. There's a bunch of O's in the top. There are four O's in the top layout here, the one with the two emojis, and those were uploaded in GPU memory once. I mean, it's all uploaded all at once. All glyph data is all at once, but like that only exists in one spot in GPU memory for that specific font size and font color and that specific glyph, and it's being used in all four of those locations. So basically, we're deduplicating the glyph data, effectively deduplicating the glyph data, so we have to upload and use less in GPU memory each frame. That's cool. The second thing is that we have a CPU side cache, because if we had to re-rasterize every single glyph here, even skipping those we've already rasterized that frame because we already know this in GPU memory at that point, this would be dog slow. This would be dog slow. This text specifically would take about 30 milliseconds if I was doing that in a debug build. About 3 to 4 milliseconds in a release build. That's not okay. So the CPU side cache will keep around a rasterized copy of each glyph for the entirety of the program's runtime. So as soon as we hit that O for that specific font size and color, we rasterize it, put it in the CPU cache, and never rasterize it again. So that means the only work that's being done to render this text right now, every single frame, is to copy some bytes from CPU memory into GPU memory, and then some texture mapping in a shader, which is cool. But this text can be updated on the fly, and it will reuse these glyphs and moving them around. It's great. I'm quite proud of the code that handles the caching and the fallback and the way in which it like handles that flow and then like error states. Like, I'm really proud of it, and it's like really small and elegant and easy to follow, because I really love Rust. Honestly, Rust is great. I can show the code just because I'm quite happy with it. I'm just really happy with this specific chunk of code because it's just great. So this code right here is entirely responsible for all of the caching. Like that, like it goes out into these two functions, right? For like the actual rasterization occurs in here, and then like copying into what's going to be put into GPU memory is done in here, but like there's not that much logic there, right? But this is it. This is like the whole logic for the caching mechanism, which is super cool. So we look up the specific glyph with its font size and color in the GPU cache, and if we've already put it into the GPU cache this frame, then we have it, we're done. Here's that cached glyph. If it's not there, we insert into the GPU cache. We grab it from the CPU cache, and if we have it, we take that and we put that into the GPU cache, and then we track it, and then we return it out. But if it's not in the CPU cache, then we go rasterize it, and then that's the last time that glyph, that's the first and last time that glyph with that specific font size and color information is rasterized ever in this program execution. That's done, and it's put into the CPU cache. So this and then after that, then we can put it in the GPU cache, and we're done. So like all of that complex logic is just being handled here, and this avoids extra hash table lookups because we're using .entry and or insert with, which is just such a cool little this right here is a very, very, very powerful construct in Rust. I'm very happy with that. And this is just like some optional stuff. Like, anyway, yeah. And remember what I said about without any of that cache, without the CPU cache, even when we're not rendering duplicates, right? Even when we're not rendering rasterizing duplicates of a glyph within the same frame, but we're still rasterizing every single glyph, font size, color combination that's used within a specific frame, that frame. This would take about 30 milliseconds in. I realize what I just said is a big jumble of words. Anyway, this would have taken, without the CPU cache, this would have taken 30 milliseconds in a debug build, and about 3 to 4 milliseconds in a release build, and like significantly more than that without the GPU cache. But with both caches, this takes about 3 milliseconds in a debug build, and it's so fast, it's well below the margin of error when you're measuring in milliseconds, that it measures out as 0 milliseconds in a release build. So yeah, I'm really happy with this. There are limitations, right? Because so I can't like smoothly scale this text, or smoothly crossfade it without like hitting performance issues, because that's how glyph rendering works. Whereas if I was, that's how glyph rasterization works. Whereas if I was doing mesh decomposition, I believe it's called, where you turn it into an actual mesh and then that's just like part of my pipeline, I could do that easily. Or if I was instead of rasterizing glyphs, normally I was generating a signed distance field and then using that to scale and color. If I was doing either of those, I would, but those are a lot more work than this, and I don't need those. So yeah, well, the first time the text scales, it'll be slow, but then after that, it'll just be hitting the cache. But yeah, there are limitations to this. But I would feel extremely comfortable shipping a game with this tech stack. Yeah, because like I control all of the APIs. I control the game that's being built with the APIs. I've built the specific support and features that I want, and I can avoid those that I know are going to be a problem. And if I need to have those not be a problem, I can just rewrite it. But I know like the sort of stuff I want to make. And one last thing I want to show off, because I really like this, is if I come over here and I have that first text, and I render that with a bit of alpha transparency. This is going to take a moment. I'm on a significantly slower machine right now, so this is going to take a moment. These warnings are not in my code. These warnings are not in my code. I'm using a very immature library for this. But any moment now. It's probably linking at this point. There it goes. Okay. So here we have some alpha transparency, and you can see as I move it around, like the that top layout, you can see stuff through it, but also with the emojis, which is like I'm quite pleased with, because the way I'm doing alpha blending is just like, it was just like just a few extra lines, like 3 extra lines to handle it for bitmap emojis. So like I just did. Yeah. I'm just pleased. I'm pleased with it. And the alpha transparency is included in that color information. So like different alpha transparencies are like part of like how it gets cached and stuff like that. So because it's all like part of the rasterization. So yeah, I'm very pleased with this. I am just so happy with it. Next, I want to work on UI, which is a requirement for me to start working on a level editor. I want to start playing around with audio soon. Start getting some debug overlays working. I have some really cool ideas for some debug mechanisms that I really want to play around with because it's just super cool and super nerdy. But yeah, that's it. Thanks for watching if you enjoyed it, I guess. Cheers.